Hello, I am Dr. Michael Greaves, and I am the Chief Scientist of Advanced Manufacturing at the Florida Institute of Technology. And I am here today to talk to you about the future of additive manufacturing. And my focus is going to be talking about where are we going to be going, do I think, in terms of where additive manufacturing, and in point of fact, how it's connected to the virtual world. And I just want to sort of start off by saying that we need to really appreciate the advances we are making in technology with respect to computer storage, communications. And the projections are that in 2030, we'll see a 64 times increase in the capabilities we have now, which are pretty impressive. But by 2040, it'll be an 8,000% increase. And so times increase. So the whole idea here is, as you can see, from the beginning back in the early 1970s, we're looking at a logarithmic exponential increase in capabilities, which means we want to try to leverage our use of those capabilities in terms of all of the product development and manufacturing. And so what's interesting is that the digital twin, which is this idea of having a virtual version of your product, and additive manufacturing are complementary technologies that are working in tandem. And they have a lot in common. They've both been around for a while. I introduced the digital twin concept in 2002. In fact, didn't even have a name at that point in time. And obviously, additive manufacturing in the form of stereolithography has been around for a long time in creating prototypes. But in 2015, they really started to take off as core technologies in terms of being able to really utilize them, not only for kind of obscure or small aspects, but in terms of a major production. And the kickoff in digital twin was this article in The Economist that basically introduced a digital twin as an idea that it could be the 21st century approach to productivity enhancements. And one of the key parts of this was a comment by John Vickers, who is NASA's principal technologist, and he said, the ultimate vision for the digital twin is to create, test, and build our equipment in a virtual environment. Only when we get it to where it performs to our requirements do we physically manufacture it. And so this is this whole idea of being able to move work from the physical to the virtual. And I would add to his quote that what we really like to do when we get it to where we want it to perform our requirements in the virtual world is we really would just like to print it. And so this is where additive manufacturing really kind of works in tandem with the digital twin and how we really are connecting these two concept technologies together to really improve our capabilities in being able to create, build, support new products, and basically being able to do it more effectively and efficiently. And just so for those people that maybe don't have a real good feel for the digital twin, there's really three components. And this was actually introduced back in 2010, had a different name, but it was a digital twin model at basically a conference for the AIAA in terms of product lifecycle management and the quest for sustainable space exploration, presentation that we did out of NASA Marshall Space Flight Center. And there's three major components to the digital twin. One is that there are real products in real space, which we have always had. And so these are the physical things that we've made, since time immemorial, that basically have move around atoms and to create the product that we need. The new piece is this idea of the digital twin in virtual space and having basically this digital version of the physical part of this, and being able to then, in the third piece, connect it to taking data from the real space to make our virtual space digital twin, and then using that information and be able to do things more effectively and efficiently in real space. And so this is sort of the concept that's really driving how we want to do products in the future is be able to create, test, build, and operate in virtual space. Why? Because bits are much cheaper than atoms and are getting cheaper every day, as you can see from my slide on the increase in capability. And in point of fact, moving around atoms gets more expensive if simply by the inflation rate. What we want to do that basically is after we do everything in virtual space and have our product that we have an understanding of not only how it's supposed to work, but how we're supposed to make it and operate, we then want to print it. And so this is where additive manufacturing comes into play, is this ability of being able to do as much work as we possibly can over on the right side. And then when we get it all right, we want to basically go out and print it with additive manufacturing. And so the framework of how we sort of decide to do that is what was done by Dr. Susan Smith, who was the chief scientist for advanced manufacturing at General Motors. And we came up with this concept called the SAM-CT framework. And SAM stands for size, accuracy, and material, and CT stands for cost and throughput. And so we need to ask these two questions that will determine whether or not we can actually use these technologies. And one is, can I build it? So can I basically have something that will give me the size, accuracy, and material that I need for the product that I want? And then, should I build it? So is it cost effective? Can I build it fast enough being able to do that? So kind of an example is I can build an engine block using additive manufacturing, and it cost me $5,000. Unfortunately, I can cast it for $500. So the can I build it answer is yes, but the should I build it would be the answer to no. But as we're seeing over time, the more things that I can build, I should build it because we're becoming cost effective. And so this whole idea is what's going to be driving additive manufacturing with its digital twin virtual components is, can I build it and should I build it? And so looking at an additive manufacturing overview is that additive manufacturing is a rapidly advancing disruptive technology. And what's a disruptive technology? Basically, it's a whole new population of consumers and users at the bottom of a market access to a product or service that was historically only accessible to consumers with a lot of money or skill. And so examples of that are cell phones, PCs, hydraulic excavators, is that basically the old technology were landlines, mainframes, and wire excavators. And at the point in time that these new things were created, they really weren't financially feasible except for a very small group. I remember in the early 70s, my boss had a car with a phone in it, but it wasn't a cell phone, and it was pretty awful and expensive to basically be able to use. Today, obviously, everybody has one. So I view additive manufacturing as a disruptive technology. We're basically looking at the scope in terms of how we are capable of moving into a variety of areas. So it started off in classical manufacturing, automotive, and aerospace, but we're moving into areas like prosthetics, dental, food, housing, pharma. So the scope of this is changing pretty dramatically in terms of who can use this kind of technology. The scale is also increasing pretty dramatically. So at the beginning of additive manufacturing, we could basically create things at a pretty small scale. I have promised the Navy in 2075 they can print aircraft carriers. I have told them that if they're not happy, come find me. They won't be around, I won't be around. But I don't think it's out of the possibility that we can basically create things at a large scale. Now, whether we actually have aircraft manufacturers or swarms of ships that work together is another question. But this whole idea of the fact that scope and scale are increasing. We're also seeing a constant stream of new announcements of material, processes, size, and speed. And so the technology is moving pretty rapidly in terms of being able to have new materials, new process capabilities, as I said, bigger size, and basically faster speed and being able to develop this. And so the whole thing here is going to really determine, though, is that how do we basically design and create these new products. And this is going to require what I'm calling DFAM, and I think it's called that all over the place now, is that design for additive manufacturing. So we're going to have to integrate the design piece with the manufacturing piece, which we historically have not done. And so it's going to impact functionality, structures, and component complexity. But understand, it's just not a technology issue. It's going to require a change in culture of, in essence, how we design and manufacture products, how we test products, how we educate the engineers and manufacturers of tomorrow in the universities today in terms of how this is going to work. And so it really is a change in not only the technology, but in this how we think about products and how we think about the capabilities and their manufacture. And so in terms of the AM hierarchy, where are we going to use these things, additive manufacturing, as we move along? And certainly we do prototypes, and we've done that for maybe the last 20, 30, maybe even longer in terms of being able to produce a prototype of some sort of product using additive manufacturing or one of its predecessors. We're going to move into fixtures, molds, and tools because they're low volume and they're custom products, and I think that we're starting to see ability of being able to do those sorts of things relatively quickly, and in fact more inexpensively than we've done in the past because of the long lead times for some of these things. And so we're starting to see these things be done additive manufacturing. Parts on demand. So if I'm in the field and I need a part, I basically can print it out as opposed to wait for it to be shipped. Military is obviously very interested in that, but all kinds of even spare parts depots, all those sorts of things could go away if I can basically print parts on demand. One of the first uses was we sent a printer up to the space station because the UPS charges are really high to get something up to the space station. And so the ability of them being able to print, I think the first thing they printed was a wrench, was certainly a big opportunity to do that sort of thing. We're going to do it on designed and engineered products where we have the blueprints and the models. And certainly we can reverse engineer things to where we don't have the information in order to be able to print that. Existing production parts, same sort of thing, designed and engineered, reversed engineers. I just don't think that we're going to see a huge amount of that. My guess and the guess of people that are in this area is that maybe 10 to 15% of existing parts really can be done with current additive manufacturing technology. I think that'll increase over time, but I basically see the real big opportunity is that it's going to be designed for additive manufacturing parts. And we're going to see such things as lightweighting, being able to produce lattice parts where we produce the solid part, same structural characteristics, but with a lot less weight. Reduce part count, so being able to reduce the part count of assemblies and be able to dramatically change that and produce the part as one part. And then finally, functionality not previously available. So for example, being able to put cooling tubes in solid pieces of metal where we really couldn't do that, or lattice networks with inside a solid piece. So we're going to see these three things that are going to drive our design for additive manufacturing to produce things that we previously could not produce. I think it's going to be driven by new materials, the ability of basically determining what material you really want, designing that material, and having custom hybrid combinations that we really couldn't do in the past, and being able to then print those capabilities out. So what are the DFAM needs? I mean, what do we really need to basically be able to do that? We need new design rules. So the design rules of the past are not going to be applicable to some of these things that have different characteristics and capabilities that we've been doing previously. It has new design implications. So deformation of the product is going to be different. We have isotropic issues. So how does the material structure in terms of that? Surface finish, how do we basically handle different surface finishes because of the fact that we're printing it? We're going to have design rules that are tied to equipment and processes. Today, we really don't care pretty much what milling machine it's on. But in the future, the different types of machines with size and capabilities is going to be extremely important. And as an example of that, we did a test kind of system for SME with basically a DFAM machine selection. So you could select the kind of machine you wanted, the kind of processes you wanted, the kind of materials you wanted, and it would show you the types of machines that were basically applicable to the design that you wanted to do. And so this was a demonstration project, and it worked fairly well. And that's what we're going to have to see in the future, is this ability of building in your machine at the time of design, which obviously is very rare today. So that's part of the DFAM issues. We're going to have basically new quality examination and capture standards. And so this whole idea of how do we basically develop our quality control is going to change, because we're going to have to do things differently. And so we're going to need new validation, verification, certification standards, methods, and as importantly, culture. So if the issue of it is that you have to do 10,000 coupons to verify something, when you're doing additive manufacturing and every part is I won't say totally unique, but kind of unique, is you're not going to be able to do that. And so we're basically going to have to change how we think about validation, verification, and certification. And that is going to really require a change in culture in the testing community. Custom materials, as I said, I think this is going to drive where we're seeing our business going in picking a material that really is what you want and being able to then print that out. So it is related to additive manufacturing, and eventually will drive AM equipment in terms of picking the equipment and then picking the custom material and then driving the equipment that we're going to use. And then we're going to design specific material characteristics for specific performance. So we're actually going to basically pick the material that's going to give us the performance that we want. And that will probably also simplify some design characteristics in terms of being able to rely on the material as opposed to having to rely on the particular shape itself. And I think that we're going to see multi-materials come into play of being able to merge and match different materials. So what are the impediments to this? I mean, because this is always kind of the issue in terms of new technologies, is that there are impediments, both technology and culture, that cause us to not adopt these things quickly enough. One is functional siloing. So the classical thing of designing the product in engineering and throwing it over the wall to manufacturing doesn't work if I'm doing additive manufacturing. Engineering and manufacturing have to be completely integrated. Traditional university education. I mean, we're basically educating the students in this standard way of doing things. And so a lot of universities really don't even talk about manufacturing, but manufacturing is going to have to be a key component in terms of my design capabilities. And it's going to have to be integrated, and we're going to have to design for particular processes and technologies. Certification and testing. And so how do we basically test a product that basically is created kind of a one-off in an additive manufacturing environment? And so if I look at sort of the quality hierarchy and look at risk versus cost, here's kind of how we determine whether or not we're going to basically accept a product and accept the product's risk. First of all, I can just accept the product. You ship me something, I put it out on the line, okay? It is low cost, but it's high risk in terms of the quality aspect. I can then go through a certification process and certify the product meets a certain characteristics, and that certainly gives me a lot more comfort, but my costs go up. I can inspect, and the two forms of inspection is I can do sample inspection or I can do 100% inspection, and that gives me a feel for what are the defect rates and whether I should accept it. Finally, I can do testing, which is the most expensive and lowest risk, and I can test the sample or I can test 100%. And if I really want to be convinced of it, I can do destructive testing, which basically allows me to basically test the product to destruction, and that really tells me, whether it worked or not. Unfortunately, we can't sell a whole lot of destructed samples, and so nobody buys cars that have been through crash tests, for example. So that's the whole issue in terms of the testing piece. But the cheapest and the lowest cost and the lowest risk is if I had the information about the product in terms of how it performed. So if I had all that information, I can basically be able to use that particular product, and I have high confidence that it's going to work because I know exactly. And so assuming I could see into the future, I would know that it really works the way it's supposed to. And so the current additive manufacturing problem is that we really have to, at this point in time, we do inspection at 100%. So the GE turbine blades are CT scanned at 100% in order to be able to determine whether they've been produced additively right. Unfortunately, that's fairly expensive. So my proposal to that is what I'm calling digital twin certified. And this moves into the idea that the information about the product is going to be the lowest risk and the least cost. And so what I'd like to do is capture sufficient process production data of the AM part. So as it's being produced, I capture information about sort of each voxel of data and information in order to be able to build that product and a digital twin version of that. I create a digital twin instance of that part, so I actually have a digital twin instance of that specific part, exactly how it was made, not what the design was, but exactly how that was made, voxel by a voxel. And then I test the digital twin instance to destruction. So if I can basically get that model right, and I test the virtual version or the digital twin to destruction, that gives me great confidence that the physical version is basically going to be of the same characteristics that my digital twin was. And so that gives me much more confidence than, quite frankly, any proxy test would give me, assuming I can capture sufficient production process and create that digital twin. But I think if you look at the technology pieces, we are moving in that direction. And so I see this as an ability to get around this 100% inspection testing issue that we now have in terms of additive manufacturing. And it ties perfectly in with the digital twin idea that is also coming to the forefront. So I just want to summarize sort of what the future of additive manufacturing is, and obviously I'm very bullish about how we are going to get there. And so we're seeing disruptive technology at scale and scope. We're going to have more scale as we move along in terms of being able to build bigger and bigger things, and we're going to see more areas be able to use that. Healthcare is especially an interesting one. We're seeing basically that additive manufacturing not only in sort of the implants and things, but we expect, in fact, I was at a presentation where in 20 years you'll be able to print new organs. Don't know if that's going to actually happen, but it certainly is exciting to think about that. It's going to be integrated with the digital twin. So this whole idea of moving as much as we can into the virtual world, and then when we basically create the product, test the product, manufacture the product, and support and sustain the product, when we get it all right, we actually go out and we simply print it. And then finally, it's going to be driven by this new idea of design for additive manufacturing. And so we're going to have to change the way we think about this design to manufacturing process, and we're going to have new design rules and new understanding of how these things work. And then finally, it's going to be both technology and cultural driven. And so the technology, I have high level of confidence that we're moving along the technology curve rather nicely. The culture thing is always kind of the issue that stops to this advancement, in that we basically, change is tough for a lot of people, but we're going to have to change the culture along with changing the technology. And then finally, digital twin certified, I think, is going to be an answer to how we are going to handle this idea of using information instead of doing sort of physical testing processes. So with that, I think this whole idea of the future of additive manufacturing is pretty exciting, and I think that I may be sort of wrong in some of the margins here, but I think directionally I'm focused on how we are looking at where we're going to go in additive manufacturing, in not only simply the classical manufacturing areas such as automotive and aerospace, but in healthcare, new products in terms of aerospace and healthcare and all these other areas. So with that, I'd like to thank you for listening, and I hope you'll find the additional presentations very interesting in terms of the types of things we're doing in different industries.